So just to set the basis of where we are at. So we all know, working with HRI, that for our robots, understanding human is so complicated. Actually, it's much more difficult than even doing a backflip. That can be done. They can do parkour even, but consistent understanding in a general situation what a human is going to do is very, very difficult. And that's puzzling, because for us humans that sounds pretty easy. I mean, we are born with a lot of abilities that are actually designed to facilitate this kind of mutual understanding with each other. So for us it's super simple, and this leads to a very negative, if you want, asymmetry, because we are perceiving the world and others in a very different way with respect to our fellow robots and machines. And this poses a strong barrier for us to establish a mutual understanding. And this barrier is really intertwined with the strong connection that we as humans since childhood have between action and perception. Indeed, what we can say is that in some sense, we see through the lenses of our body. We have a sort of anthropomorphic view on the world. And this has very strong neurophysiological basis. So we are aware of the finding of the mirror neuron system. That is, that there are areas of our brain that are responsible not only for the generation of our motion, but rather also for us understanding, mapping the movement and the actions of others. And this provides a sort of direct match, a sort of vocabulary, if you want, that is built upon our ability to act, and that allows us to have a clearer understanding, even prediction of what the others are going to do. And this leads to the fact that human or humanoid motion is special to our eyes. Indeed, the way our brain control motion is a function of the structure of our body, and then of optimal principles. And this leads to consistent regularity on the kinematic, at the dynamic level. And we always reproduce these regularities when we move, but our brain is also sensitive to them when we are observing someone else performing an action. And this gives us access to cues, to information about what the action is, what is the goal, also subtle properties about the objects we are manipulating. And everything is hidden in plain sight in these regularities of the movement. And so for our brain, extracting them brings very nice advantages through mechanisms that are supported by the mirror neuron system, like motor resonance, for instance. Then we can have really automatic and emergent coordination, or we can predict and anticipate the outcome of someone else's action. And most of this happens below our level of awareness or voluntary control. It's something that our brain does for free, if you want, providing us very good advantages in terms of interacting with others. And when we are in a social context, and this was something that already Mohammed pointed out before, this phenomena become even more strongly evident in our movement. Sometimes it's voluntary, sometimes it's, again, involuntary. But we start making movements that are not any more optimal in terms of energy consumption, for instance, but they provide advantages in terms of comprehensibility and readability from our partner. Overall, this means that when we are interacting with another human agent, we are very good at reading, understanding, inferring this information, and at the same time, we are sending this information all the time with our movement alone. And what we want for machines is, of course, to be able to be sensitive to the very same signals, to be able to read us with the same facility, but at the same time also to be as expressive in their motion and action, so as to become easily understandable for us. So, and this requires then a two-side kind of task. First of all, making robots sensitive in a sense of letting them know where to look at to find what could reveal something more about our action. And there are a lot of cues that we can read. We can read, for instance, facial expression to have a sense of how a person is somehow feeling toward the kind of interaction that we are doing, and maybe use this information to adapt a training that the robot is performing, so that it can adapt its training strategy not only to the performance of the partner, but also to the, let's say, facial expressions, to the reaction, the state of the partner it has in front. But it's not only the face that provides information. The way we treat objects, for instance, can be a very good proxy to understand how we are feeling in some sense. And we can we explore this possibility, for instance, to read the style of an action. When I'm moving, I can be very gentle, very kind, I can be very aggressive. And we as humans are very sensitive to this kind of cues. We can distinguish very well if the movement is fast or is aggressive or is low versus gentle. And we found out that even from the kinematics information of the body during the performance of actions, we can have the robot do the same. So be able to distinguish between gentle, rude, or fast, slow, or normal kind of actions. But it's possible to do that even with less information. So not being able to see in the body, but just being able to read from a sensorized object how the object is manipulated. And so by measuring, I don't know, how the object is rotated or how it is touched on its surfaces, it is possible to read and understand with a decent accuracy if the person is treating the object gently or aggressively. And we can do even a little more. So we can have a sense of which kind of emotion are driving the object manipulation. Again, just by reading the information about how the object is moved, so where it is touched on its surfaces and how fast it is rotated. And the combination of these two sources of information is actually precious in the accuracy. But sometimes we don't even need, in the context of human-robot interaction, to exactly know which kind of feelings I'm experiencing. And also because it's extremely difficult sometimes to distinguish the exact feeling. On the other hand, it is pretty crucial to have an idea of how the person is feeling toward the interaction as a whole. So is it going to be desiring to continue to maintain the interaction or to withdraw from it? That, the desire of withdrawing from interaction can be driven by a number of different emotions, and the same holds for the desire of keeping an interaction. On the other hand, maybe we don't need the precision of knowing exactly what it is up front, but at least the robot needs to know whether something is going so wrong that it needs to change its behavior to foster a better comfort. And this was the idea by Elena, to try and see whether in a natural interaction between a human and a robot, we can use this comfortability item to try and guess whether something was going wrong or not. So we designed a situation, a sort of interview, in which the robot was the interviewer. It had a fixed set of questions to ask to the interviewees. We had the help of a journalist to actually design a real interview, but we tried to design it so that there were some questions and behaviors of the robot that were meant to make the person feel comfortable, and others that were meant actually to make the person feel uncomfortable. So the first, this is an example.
What is your name?
I hope you can hear the...
Wow, John, I like it.
So the robot is actually just asking questions like, what is your name? And the person is replying, where do you work at? What is your topic? Etc., etc. There are a lot of different interviews and they last about 15 minutes. But while the first part of the interview is really like very friendly, with the robot complimenting the person and asking for judgment and opinion, and then complimenting and replying in a positive manner to what the person tells. In the second part of the interview, the robot starts showing a lot of behavior that were meant to trigger a level of uncomfortability, like errors, for instance, exchanging the name of the person, or failing to understand multiple times what the person was saying, or showing a malfunction in which the robot started saying nonsensical words, or disrespecting, let's say, the opinion stated by the person. Plus, there were a few questions of neutral sentences just to let's say, make the interaction more natural, also following the suggestion by the journalist, and then some direct questions by the robot at the end of each of the two phases of the interview, where the robot directly asked how the person was feeling toward the situation. And we collected a set of self-reports about the comfortability experienced by participants on a 7-point Likert scale. And what we found out was that the actions meant to trigger uncomfortable reaction on average significantly reduced the self-reported comfortability. And that was indeed what we expected. But the interesting aspect was that when we looked at the kind of self-report when participants were asked by the robot to reveal their state, they both self-reported and replied to the robot in a way that was a bit in contrast with what seemed to be their general and average feeling of comfortability during the phase. So especially after the very negative phase of uncomfortable triggers, they still rate themselves as being quite comfortable. And if you look at the video, in this case, I removed the audio to simplify, I guess. As you can see, there is a sort of striking difference between the kind of facial expression and behavior of the person with respect to the positive feedback that she gives to the robot. And this is just one single example. We collected actually the video and the audio of all the interactions after explicit consent of the participants, also because this becomes a part of the column on the institutional magazine. These are actual interviews for journalistic purposes. But by looking at different videos, what we realized that there are a lot of nonverbal cues that can kind of reveal levels of uncomfortability, of embarrassment, of annoyance, if you want, in response to robot errors or misbehavior, also sometimes correlating with the level of self-report that participants provided. And so our intention was actually to find out whether we can enable a robot from video alone to detect moments of uncomfortability. So we, Elena actually rated, annotated all the videos in 3-second segments without audio in randomized order in terms of different level of uncomfortability. And then she tried to find out whether it was possible to build a system able to detect at least whether it was uncomfortable or not. And what she found out was that indeed, by using features related to the upper body pose, to the facial features, and combining also information about gaze direction and the head pose, it was actually possible to have a good, decent accuracy in detecting moments of uncomfortability, even though this ability reduces significantly if we start changing the participant. So now we are working in order to try and refine a way that can generalize better, or at least we are exploring different cues that can be helpful in strengthening this detection. But sometimes understanding whether the partner is comfortable or not is not enough, and sometimes looking at the face and at the body is not enough. And that's where eyes can actually help us and provide us another important input. And in the past, we used the gaze direction of a person to be able to understand the goal of its action. More recently, we tried to do a step forward and try and use the same information, but to detect an internal state of the person, which is whether the person is experiencing cognitive load, especially due to the formation or creation of a lie. So we started with a well-known psychological fact, the fact that when you are experiencing heightened cognitive load, you have a task of pupil dilation. But we wanted to know whether this kind of phenomenon could be operationalized, could be actually used in a real human-robot interaction. So we designed a sort of interrogation scenario with a robot or a human interrogator, and we studied whether we could detect by leveraging on the pupillary dilation whether the person was lying or not. And interestingly, we found out that yes, it's actually very consistent, even in this kind of settings, even in HRI. So it works also for human-robot interaction. Then we wanted to know, okay, but we usually don't explore with robots actual interrogation. We play games. So is it possible to have a robot sensing cognitive load in a more natural, interactive game-like scenario? And so we performed a task in which the robot was actually playing a magic trick. So the person had these cards in front of them. They could look at the cards, and the cards had pictures. And then they had to describe these cards either truthfully or inventing a story about the card. And the task for the robot was actually to sense that and detect whether the description was veridical or it was a lie. And there was a very nice software architecture below for which the entire task was performed autonomously by the robot, leveraging on information coming from the eye tracker, these are the glasses you see. And so at first we had the robot, the task was a sort of calibration in which participants were asked to lie only on one of the 6 cards available. And then we took like the pupil dilation that we had for each of the cards, and the robot detected as lie the one for which the pupil dilation was biggest. And with that, we had a very nice accuracy in guessing, even if it was just a heuristic, it worked pretty nice. Then we made a sort of more complex task by which we said, okay, let's use this average values as to find a threshold of pupil dilation for that participant that correspond to saying truth or saying lies. And so we moved to a second phase in which that participant was free to choose for each new card whether to lie or say the truth. So we didn't know how many lies or how many truths there were in these next 6 cards. And we used this threshold to classify. So if it was pupil dilation larger than that threshold, it was a lie, otherwise it was a true saying. And with this very simple heuristic, again, the classification accuracy was pretty nice, 70%. And if we allowed this threshold to change over time from card to card, so if we gave a feedback after each responses of the robot, then with this incremental heuristic, the accuracy raised up to 78.7%. That was pretty nice to sustain an interactive game with participants, but it was interesting also to see whether this knowledge could be then generalized to be able to guess from unknown partners. And the solution that worked best was to see the lying as a sort of anomaly detection task. So Dario trained one class SVM as an anomaly detection, lying as an anomaly, and found out that indeed with this approach it was possible to detect novel lies from novel participants with an F1 score of 67%. And the question that you could ask is that it seems nice, but how do humans fare? So how good are we in performing the same task? So if we look at the literature, we know that humans are not so good at detecting lies. So we have around 54 on average accuracy in human lie detection. But we wanted to test it exactly on the kind of task we perform. So we collected videos of our players either saying the truth or saying a lie. And we also picked videos in which our classification mechanism played by ICAB was correct, and some videos in which instead ICAB had failed. And what we found out was that indeed participants showed on our sample video about 54% of accuracy, which is very consistent with the literature. But the interesting finding was that they were particularly good where ICAB failed. So this suggested us that the way participants, humans, are actually understanding whether it is a lie or not was orthogonal with respect to the pupillary dilation that the robot was using. And indeed, we asked them which kind of features they based their judgment onto, and they were mostly features related to the prosody and to the movement that the participants were performing while telling the lie or describing the card. All features that by design our robot was not considering. And this suggests us a new avenue to actually improve our lie detection system. This kind of information, pupil dilation, can also be helpful if we don't want just to assess the cognitive load, for instance, lie related, but also if we want to have a sense of whether a person is perceiving or not a risk. And this is kind of research that we performed also in collaboration with the University of Waterloo in Canada to try and assess whether in a context of an interaction, also with the robot, we could enable our system to detect whether the person was perceiving the presence of a risk and whether it was going to accept or not the risky choice. So Dario actually developed a sort of video games in order to create situations that were able to create risk, but without being risky in the real life. And it was a sort of adventure in which there were a series of events, and for each event, the participant had to make a choice. In particular, there were some resources that the participant had, equivalent to life and private information that should not have been disclosed during the game. And then the game itself proposed several proposals or alternatives questions. And some of them were not risky. Some of them were actually risky, were threats, and they were inspired by actually a questionnaire that is designed to measure risk attitude in human participants. And then some threats were actually performed by other agents, either within the game, virtual agents. So this is the case of social engineering from a virtual agent, or from the robot that was actually physically in the room with the participant who was playing the game. And what we collected were actually both the way participants made their decisions, so whether they accepted or not the proposal, and also some physiological responses. As you can see from the graph on the left, as you could have expected, participants' acceptance rate decreased significantly in the risky scenarios with respect to the non-risky scenario, and increased again a little in the case of social engineering, so where another agent was pushing them to make a risky decision. And interestingly, as a function of accepting or refusing, indeed, we found out also a complex pattern of difference in electrodermal activity, so physiological response, and also in the pupil area. And starting from these information, Dario wanted to try and see whether we could assess or guess whether the person was perceiving a certain proposal as risky, as a form of social engineering, so a threat made by this other agent, and whether the participant was going to accept or not the threat. And indeed, after multiple different trials, they found out that especially by using pupil dilation, it is actually possible to understand whether the person is perceiving a task as risky or social engineering or not. And by basing the judgment on electrodermal activity information, it is also possible to infer whether the person is going to accept or not a social engineering threat. Why do you want to know this? Well, because then maybe you might have a robot that actually pushes you to change your mind and not accept the risky threat. And this is something that we tried with a different platform within the collaboration, with the Furet robot. And we wanted to ask whether we could have a robot induce behavioral changes in participants performing this risky adventure. And we explored the different strategies for the robot to induce the change, either a rational strategy, providing a logical explanation of why the person should change his mind, or an effective one, in which the participant is pushed to change their mind by leveraging on the rapport between the robot and the player. And we found out that in the context of a similar adventure, you could have a significant amount of situation in which participants change their mind, especially if they first accepted the risky threat and then the robot pushed them to change their mind. And it is possible also to notice some changes in their facial expression and in the mouse trajectory while reading the replies, especially when they are trying to keep, not change their mind after a rational explanation by the robot. So you can see by monitoring the mouse trajectories and the level of valence and arousal expressed by participants in this context, you can see the significant difference between these two choices, so changing my mind or not changing my mind, but only in the rational situation. And interestingly, by knowing that, we realize that it is also possible to predict whether a person is going to change their mind by monitoring their mouse trajectory. Even just monitoring the first half of the mouse trajectory allows the computer to know or to guess with a decent accuracy whether the participant is going to change their mind or not. So, of course, this refers to the possibility to understand, to read, to be sensitive. On the other hand, as I told you, humans are also very good at being expressive, communicating, and we have the need for robots to be as understandable as well. So this requires ad hoc research. So we tried, for instance, to study how to express attitudes, this famous being gentle or aggressive, and capturing the signature of what makes a movement aggressive or gentle is not easy. But if you do it right, even if you're not seeing the face, and even if you're seeing a clear robot moving, still your brain will show a similar pattern of activation after seeing the robot expressing attitudes than after seeing a human expressing attitudes, which means that we can reuse the very same mechanisms in our brain that we normally use to understand humans to make sense of what a robot is doing. And these have strong behavioral consequences, because then we notice that when the robot is moving aggressively, or even just pointing aggressively to an object, then the human will move toward that object more aggressively. And this doesn't apply only to humanoids, by the way. We performed a very similar task with the manipulandum, so just an arm, performing physical disturbances on the hand of the person, but we found the same results. So if the robot moves me aggressively, I will start moving aggressively, and vice versa, which tells us that subtle modulation of how the robot moves are sufficient, even in the most simple task, to change the entire tone of the interaction. And it's not just the emotions or styles that matter. With our movement, we reveal also information about the objects we're handling. So we explored, for instance, how to allow a robot to reveal with its movement alone whether an object is to be treated with care or not, and not just by retargeting human movement, but rather with a generative approach, so that the robot can generate novel actions, but that still maintain the signature of careful or not careful. And again, we started with a humanoid robot, but then we replicated the very same task with less humanoid platform. And more recently, we have done that with a Kinova arm, showing the very same results, suggesting that these features are really working very well across multiple environments. And motion is a precious source of information. We can use it also to reveal how the learning of the robot is ongoing, maybe coupling it with information derived from the way the robot moves its eyes and also with the facial expression. But we have to be particularly careful because we found out that this kind of sources of information for the human do mean different things. And so not all of these signals coupled together will work fine. And so future research is actually needed to find the proper way to make the robot legible, understandable, and predictable without actually making it more complicated and less understandable for the humans. And this might entail also changing the learning process. And this is something that Mohammed already explained nicely, but we are exploring different ways to make the learning process itself more human aware, maybe taking into account the elements that go beyond performance, but maybe take into account also aspects like rivalry, which is usually not considered in competitive learning agents in reinforcement learning, but it's very, very common in human-human interaction. So these were a few examples of how to make the robot sensitive and comprehensible. There are so many more we have explored. There are so many more that other people have explored, but this is just action and perception. But why I was mentioning that we need to go beyond that? Well, because these are the elements, the little elements that we will need then to have coupled together into a unifying architecture, which will base itself on action and perception, but will need also other important skills, including memory, including internal motivation and internal drives, internal simulation, to allow the robot to go beyond the short-term one or single encounter, but enabling it to autonomously learn and adapt to the partner over multiple encounters. And this, for instance, might require considering and reconsidering the role of affect and the role as not only as a way of reading how people are feeling toward the robot, but rather also as an internal drive for the robot itself, a state of comfort, maybe drawing inspiration from the hormonal mechanism that regulates our own decision making, to try and enable the robot to have its own autonomous goal and make its own decision by taking into account and synthesizing the history of the interaction with the partner and with the environment. We are trying this avenue. Or even if we consider more application-oriented tasks, like having a robot able to deal with multi-party interaction in natural HRI, then action and perception are crucial, but are not enough. We need to have an architecture which is much richer, because we need the robot to be able to make sense and tidy up the whole series of inputs that belong to its own self-experience. So, for instance, being able to collect audio and images of the people it met, but at the same time being able to store them in a proper way so as to be able to learn from this data over time, which means then not only collecting first-hand sensory experience, but sort it into long-term memory, establishing a learning that maybe also requires some degree of forgetting, and then also designing actions that can facilitate and foster and scaffold the learning so that the participants will provide the right information to the robot. This is something that Julia Beljovin and Jonas Gonzalez have explored with a little experiment in which the iCub was acting as an assistant. So participants could go there and ask for the menu of the canteen, for instance, but the robot was localizing autonomously, participants finding the faces, storing the voices, understanding whether it was an identity or a person that the robot had already met or not, and then use this information to save and store face and voice data to perform autonomous labeling and creating of the embedding, and then using this information to start out a conversation. This way, they ran the experiment for like about 9 days. They could actually create an autonomous data set without human external labeling. The robot started to be able to recognize faces, even though, I mean, you can see the low level resolution of the cameras and the very high intra-class variability that there was. So, and over time, it could also learn to recognize the partners with a decent detection and identification rate and false alarm rate. And interestingly, even if they started with a pre-trained model, they found out that fine-tuning with the model with a robot first-hand experience, so with the data it collected with its own eyes and ears, was actually positive to create more discriminative embeddings. And they also explored methods for allowing the robot to take this approach over longer periods of time. So also approaches of continual learning, where you're not reusing the entire data set of the time, but you're assuming of extracting some relevant information, showing some promising results. So already in this kind of a task, we see that action and perception are crucial. They are fundamental to collect the right information and provide the right feedback, but they are not enough. And they are not enough if we're looking toward adaptation, which is what they performed with the very same architecture with a tiny variation, in which they used the robot this time as a trainer for a yoga pose. So the robot was showing yoga poses and was monitoring the yoga poses performed by the pupils, and was evaluating autonomously whether the performance was correct or not, and providing suggestion and correction. And interestingly, this kind of approach and architecture allows two different horizons of adaptation: real time, in which the robot can correct in real time what the person is doing, but also long term, leveraging on this learning of who is in front of the robot at each encounter, allowing personalizing the teaching, for instance, remembering the names, remembering the right training for each pupil. And this is more or less what we believe it's important to go towards. So, of course, we need human-inspired or human-aware, better said, action and perception skills in the robot to allow the ability for the robot to interact with every human and with each human individually. But on the other hand, we also need for it the ability to learn over time, to adapt, to personalize, while keeping also its own identity or some predictability of its own behavior. The final ambition, this is my conclusive comment, is always to have more humane robots, where humane doesn't mean robots that look like us or just mimic us, but that they are considerate of us, so that they know or have an estimate of how humans perceive others and the world. And a big thank to you for your attention. A huge thank to all the wonderful group and the collaborations that allow us to perform this kind of research. And if you want to talk more about these topics, and in particular about cognitive robotics in general, I would really like you to participate to two important initiatives. One is the ICOP, an initiative really aimed at defining a common cognitive architecture for unembodied artificial systems. And it's a very widespread discussion on what we need to achieve that. And the other invitation I make is please join the Technical Committee for Cognitive Robotics on IEEE RAS. We are really committed to try and foster links between robotics, cognitive science, and artificial intelligence. And of course, there is the need of hearing more voices and young voices, providing new insights on how to do that. With that, I want to thank you again, and this concludes my presentation.